Hi, Vicky.
Hi, Shane.
I wanted to ask you today, are you more of a warm weather person or a
Ugh,
cold weather person?
cold weather person.
All right, I
I
guess
am the sweatiest person.
Oh,
Not when I was a kid, but
just now,
now it's too
adulting is
hot. I
hard.
can't handle it. Yeah,
What
exactly.
do you have
Cold
any
weather.
do you have any like special cold weather memories or like winter memories or anything like that?
Oh, a ton. But I lived in Vermont for
Hmm.
a while in the 2006 era, and I worked at a law school, and they used to
Ooh,
have they had this crazy Winterfest.
okay.
Like crazy. And I don't know if it was a rule or if the law students just took pity on the staff or what the situation was, but every Winterfest team had a couple of staff members on it as well.
Okay.
So I got to like act like a kid and run around in the snow and do all sorts of wacky stuff. But one of my favorite things, and I think about it often for some reason, is I played broom ball
Okay.
on like a very classic like town green in Vermont in the middle of the winter. So they had like built like citizens had come from their house and like built a skating rink in the middle of this green, and we played broom ball on it. And it was just like one of the various like many things I did when I lived in Vermont that was so outdoorsy and community wise and special. But have you ever played broom ball?
I haven't, but I'm just like envisioning this, and I mean this in a very positive way. But that's like one of the most northeastern things I've ever
Yeah.
heard in my entire
Yeah, I was
life.
just, like, running around in my shoes,
Yeah,
obviously, on the skating rink, and
rink.
yeah, I don't know. But hitting a ball with a broom that I just, like, found in the closet at my work, you know?
Oh,
And it
that's
was
lovely.
it was lovely. But I'm very competitive too, so I was knocking people
Ooh,
over and stuff, so
I would love to see
yeah.
a video of this, but I doubt that that's
Maybe
out there in the world.
we'll replay it this winter.
Perfect.
Yeah.
So I'm also very much a cold weather person, but I do have a very I was just thinking about this before. I have one very kind of special intense heat memory. So
Mhm.
this I was going to say this past summer, last fall of what was last year? 21. My partner and
Yeah.
I went to the Southwest on a vacation. We traveled like through all these beautiful parks. Like we're big national parks person people, and actually we got engaged at the Wave. Which is this beautiful sandstone structure in the middle of
Oh, okay.
desert, and yeah, Google it. It's absolutely beautiful. And so it was going so well, but we were camping in Zion, and Zion's like in the desert,
Mhm.
and it was hot. I
I
mean,
believe it.
at night we're talking about the lows would get down to 80, and I was like at 5 in the morning. And so the day we got engaged, like we came back from this amazing hike, and we're sitting at this restaurant and we're camping out that night. And I am so happy, but also so angry because I know we have to camp out one more night. I'm just like,
Oh, okay.
this is going to be such like a crappy end to such an amazing day. And my partner looks at me and she goes, Shane, we are adults with jobs and incomes. We don't have to camp. We can get a hotel for the night. It is literally something like in my
My
30, however old I am, mid 30s years of life. I never contemplated that you can just like buy your way out of something. I was like, of course I can.
Oh,
I'm an adult. This is amazing. So we stayed at like an econo lodge or something, and it was like the best experience I've ever had in my entire life.
the best
So
hotel you've ever stayed in, I
it
bet.
was amazing. So yes, I like it would have been a fine night. We had a great day. It was a great experience, but that hotel just made it that much better.
And maybe that also cemented the whole proposal thing. You're like, "You know what?
Yeah.
This is right.
This
This in this moment, this is right."
everything came together. I'm very appreciative. Science is fascinating, but don't just take my word for it. Join us as we hear stories from scientists for everyone. I'm Shane Hanlon,
And I'm Vicky Thompson.
and this is Third Pod from the Sun. All right. So, regardless of my probably only quite fond memory of extreme heat, I got to say I am not excited about summer, especially because it seems like every single one gets hotter, and there's this La Nina this year, and that's not going to help. But aside from my specific take on awful DC summers. We're going to talk about climate in a much broader perspective. And so to tell us more, we're going to bring in producer Devin Reese. Hi, Devin.
Hey, Shane.
Okay, so before we get into it, how are you feeling about this impending summer? You're local as well in the DC region. So what's your feeling?
Honestly, I am wishing I was on my way to some icy place, maybe like Antarctica.
Oh, me too. But climate change, right? So the poles are melting.
Well, that's true. And actually, today we're going to hear from Brian Huber, who's going to tell us about Antarctic ice or lack thereof.
Oh, so we are talking about melting ice.
Yes. Well, and no, it's about how Antarctica got its ice, which is sort of the opposite story of what's happening to the ice today. Brian Huber studies climates of the past.
Ooh, and so that could potentially tell us about what's happening now and what's going on in the future. Cool. All right, let's get into it.
My name is Brian Huber. I'm a curator of Foraminifera, which are microscopic fossils that make a shell and have an ancient fossil record, as well as they're out alive today.
Okay, so you mentioned a word that I think a lot of people may not be familiar with, and you said it quickly, and I think the word was foraminifera. Can you tell me a bit more about what foraminifera are and why that would be your way to study ancient climates?
Sure. Foraminifera, or forams for short, are single-celled organisms that are protistans, like an amoeba, and they make a shell. And it's their shell that gets preserved in the fossil record. Foraminifera have a fossil record that goes back 540 million years, but they still live in the ocean today, so they can be studied, and you learn a lot about their life habits by studying them today. I look at the evolution and extinction of different species of forams and analyze the chemistry of their shells to reconstruct ocean temperatures throughout Earth history.
Brian, how did you get interested in ocean temperatures and Earth's past climate?
It's kind of a gradual process of being interested in the Earth and conservation of resources, because I grew up in the early 70s in the energy crisis. And okay, what can we do? What can I do about this? And then just interest in studying the deep past. I applied to work at the Ohio State University for graduate school at the Institute of Polar Studies. And I just chanced into an opportunity to go to Antarctica during my first year of master's. And I went to a place that had first been visited by a captain and his crew of the whaling ship Jason back in 1892. And they landed on Seymour Island, Antarctica, which is in the Antarctic Peninsula, about 65 degrees south latitude. And they started walking across this island, which was snow-free during the summer of the south. And they came across fossil wood and fossil leaves, and then eventually came across ammonites, which are an extinct group of squid-like organism. And they brought these back to Norway in 1892, and that caused a big stir. And then there was a Swedish-Norwegian expedition to winter over in 1901 to 1903, and they did a lot of exploration and eventually published on these fossils from Antarctica. And the big news was, of course, Antarctica was much warmer than present day. I mean, there were trees, there were forests near this island of marine sediments just to the west.
And they said, wow, this is weird. We're in icy Antarctica, and yet there are fossils of these organisms that could never live here under these conditions. How did you even withstand the icy conditions during your field work?
So we went down by icebreaker. We got flown by helicopter onto the island. And we had to have support, of course, to get us off the island. We stayed in tents 5 to 6 weeks at a time. The wind was very cold, and it was quite a harsh climate, and you look around and see no vegetation anywhere. And it's just barren, exposed sediments that used to be underwater. And so this contrast of experiencing the extreme cold, yet finding things like cold-blooded reptiles, plesiosaurs and mosasaurs, as well as seeing the fossil wood, fossil leaves, it just embedded in me an impression of, and a curiosity of how much more warmer it must have been during the geologic past. Fortunately, the sediments had a lot of foraminifera, and between Carlos and I, we were able to map the island and identify the asteroid impact layer from 66 million years ago that caused the extinction of ammonites and plesiosaurs and mosasaurs, which we also found on the island.
So you're telling me that these, can I call them forams for short then? And you're saying that they're tiny protists, these tiny organisms. They have shells, and that you are using their shells to understand climate. So how does a foram shell tell you about ancient climate?
Well, as long as the shell is well preserved, they contain the chemistry of the ocean when the shell was mineralized. And there's a couple things that we can measure from those well-preserved shells that tell us about temperature. One is the magnesium-calcium ratio, and the other is the isotopes of oxygen 16 and 18. And so the forams that I study and use most for reconstructing past temperatures are with these so-called oxygen isotopes. The ratio of 16 to 18 decreases as the ocean is warmer, and then increases when the ocean gets cold.
This is fascinating. So the chemistry of ocean animal shells shows ocean temperatures, right?
Right. It sounds like these forams are little thermometers, only based on magnesium-calcium ratios and oxygen isotopes instead of mercury.
And that's wacky that their shells keep a permanent record of temperature. But how do they measure the data from these foram natural thermometers?
So when using an instrument called a mass spectrometer, we can determine those ratios and identify when the ocean was warming and when the ocean was cooling. There's a temperature equation that you can plug in these oxygen isotope ratios to, and that provides you with the estimate of actual temperature of the ocean. So you can look at detailed changes of temperature over the course of hundreds to thousands of years, or you can look across millions of years time scale.
Okay, that's incredible. So these are all kind of stacked up down in the, in the seafloor or on land in what used to be ocean, and then you're analyzing their chemistry, but you're saying that there's enough known about these oxygen isotope ratios and this magnesium that you can diagnose how warm the ocean was at the time that foram was living.
Sure. There's two kinds of forams. One is a kind that floats, and that's called planktonic. And the other is one that lives on the sea floor, and it's called benthic foraminifera. And of course, when you are studying samples that contain both planktic and benthic foraminifera, you are able to measure the temperature of the ocean surface at the same time as the temperature of the ocean floor. And so you're getting these paired measurements of ocean temperature history through millions of years. And the closer spaced your samples are, the higher resolution the temperature signal is going to provide you.
How do you sort them all out from the samples?
So to prepare the samples, you have to wash the mud through screens, fine screens, and then what's collected on top of the screens are the foram shells. And then you have to identify individual species of forams, including the benthics versus the planktics, and put them in their own little containers. And those are analyzed separately. And what's kind of cool is there different species of planktic forams actually lived at different depths in the ocean mix layer. And so you can see these offsets in temperatures that represent where the planktic forams actually lived, even though you're dealing with samples that might be 80 million years old or so. So it's a pretty cool tool, not only for looking at ocean temperature history, but also looking at vertical temperature gradients and the stratification of the ocean at different times in the past.
Just to clarify one more thing, then, you can tell by looking at the morphology, the shape of the forams, which ones were living on the ocean surface, the ones that you're calling sort of the planktic ones, and which ones were on the ocean floor, the benthic, just by the way the the foram looks?
Generally, planktic forams tend to have somewhat more inflated shells, so they're more what we call globular, and ornamentation that surrounds the shell very evenly. Benthic forams tend to have smoother surfaces of the shell, but it's not universal, and so there are exceptions. Some planktics actually look kind of benthic. So the easy to tell ones look like little golf balls. The ones that we might have been a little bit uncertain about, you can actually do comparative measurements of the specimens from the same sample.
It makes me laugh because your work is very sophisticated scientific work in terms of, reading the chemistry of forams and sorting this all out. But at the end of the day, it's kind of starting with skills that you learn in preschool to sort things through sieves.
Yeah, right. And we get to play in the mud. That's right.
We do. What did the forams from your trips to Antarctica tell you about whether it was icy in the past?
So I visited Antarctica 3 times between 1981 and 1985, and we systematically mapped the Cretaceous through Paleogene part of the island. So from about 73 million years ago up until about 56 million years ago. It was much warmer than present day. And in fact, we published the first temperature estimates of Antarctica from that time. And the temperature estimates that we got from the planktic foraminifera were about 10 to 12 degrees centigrade. And so, it's not hot, it's not tropical, but it's warm. So, that would be in the 50s Fahrenheit. And so at no time was there a major ice sheet.
Was that the warmest it got in Antarctica? Kind of like early spring in the DC area?
The warmest part of the Cretaceous occurred about from 94 to 83 million years ago. But what's exciting is just a couple years ago, drilling in the just in the edge of Antarctica through the seafloor into Cretaceous sediments, recovered a lignite, which is like a coal, that had roots of plants and a very diverse assemblage of pollen, over 62 species of pollen, recovered at 82 degrees south paleolatitude. So this is very close to the pole, verifying just how warm this peak greenhouse warming was during the Middle Cretaceous age.
If you had to picture what the ecosystem looked like based on that discovery, can you give us a visual?
It's very diverse and very green and thick, with lots of cycads and various, you don't have the kind of northern hemisphere angiosperms as we're used to. So it's kind of a primitive looking forest, but very swampy, with lots of evergreens and deciduous mixed forests.
So swampy and green in Antarctica.
Right.
That is quite an image.
It really is. Thinking about how different Antarctica was during the Cretaceous, not an icy place at all.
It certainly gives perspective on really how much Earth's climate changes if you look over that long time scale.
Yeah, and it's remarkable how we've figured out how to track climate millions of years back. But why the changes?
So can you tell me a little more about how scientifically, how people figured out that that's what caused this greenhouse hot period?
The warmest part of the Cretaceous occurred about from 94 to 83 million years ago. And this is a time when we had major volcanic eruptions in the deep sea floor of what are called large igneous provinces. And the volcanic gas erupted, produced a lot of CO2, which of course is a greenhouse gas, and that outgassing led to this warming. And it took, hundreds of thousands, millions of years for the algae and plants to sort of resorb that carbon and for it to get buried, bringing down the temperatures. Well, there's been more and more evidence of study of this time of the big increase in warming, where there's an element called osmium isotope ratios that are directly related to volcanic outgassing. And when those ratios go negative, you have major volcanic eruptions. And one of these events that triggered this peak warming event is called Oceanic Anoxic Event 2. And this occurred at 94 million years ago. It's very well dated from radiometric dating. And my colleague who has published a really cool paper, he's got a paper in review actually on this, has demonstrated that the osmium isotope ratios start going negative, and then you have ocean acidification, meaning the ocean is very acidic, and then you get what's called a black shale.
So at least during this period we're talking about, it was really a carbon phenomenon, the climate. And you mentioned these black shales.
The black shales occur, first of all, because you don't have the calcareous plankton that is normally in the sediment and in these deep ocean environments, because it's dissolved. But also the nutrient influx from the volcanic outgassing causes high plankton productivity. So a lot of organic matter is being produced up in the upper ocean. And that organic matter sinks through the water column, and there's so much of it that it overwhelms the amount of oxygen that's in the ocean. And the organic matter that normally gets eaten away by oxygen sinks all the way to the seafloor.
There was this particularly hot interval from 94 to 83 million years ago. But then even after that, it was still warm. And yet today we're looking at this icy Antarctica. So when did another change occur, or was it just gradual?
It was gradual, but with some warming blips. And so what's really neat is the Cenozoic, so the last 66 million years, is really well studied for climate change. And the reason for that is the more recent record we have in the deep sea, the more detailed it is, because the sediments are worldwide. Further back in time we go, like in the Cretaceous, the fewer places we can go to get those records. And during the early Eocene, it's warm, and then you see it start to cool, and then you see a warming blip in the middle Eocene, 44 million years ago or around there. And then it continues cooling, and what's happening is you're getting burial of carbon through shells and through absorption or from photosynthesis, and organic matter from leaves and trees getting buried, and organic matter from the ocean also getting buried. So very gradually the CO2 is pulled back out of the atmosphere, and because of that, you get this cooling over the long term. And so ice gets to sea level. Our first real record of a permanent ice cap is at about 34 million years ago. But there were ephemeral ice sheets that reached the ocean within some millions of years before that. And so occasionally the ice sheet would grow, reach sea level, and icebergs would go out. And what's neat is you have a physical record of what's called ice rafted debris. And that is sediments eroded from the Antarctic continent that get into the ice because it's bulldozing across the continent. The ice reaches sea level, breaks off as icebergs melt, and then the contents of those icebergs, which includes ice rafted debris, sinks to the seafloor. And they're really weird extraneous sediments. They don't make sense in the surrounding clay and tiny plankton shells. You might have pebbles and things that have what are called chatter marks from physical grinding. And so you've got this record of ice rafted debris in combination with the oxygen isotope, magnesium calcium ratio, and other temperature indicators of rapid cooling at 34 million years ago at the base of the Oligocene epoch.
So are you suggesting, Brian, that when you take the sediments and you run them through sieves and try to sort it all out, then that you have to sort out not only all these marine organisms, but you also have to sort out stuff that was brought by ice from land and dumped into the ocean?
Yeah, so in the locations that the ocean drilling ship has drilled near Antarctica, you're within reach of these iceberg tracks. And I was on an expedition in 1987 when we drilled the southern Indian Ocean, a place called Kerguelen Plateau, which is some 1,000 miles, I don't know, 800 miles from Antarctica. But it was along the iceberg track from 25% of East Antarctica ice sheet drainage. And so, yeah, when you use a screen to wash your samples, so the mud goes through the screen and the microscopic shells are on top. When ice rafted debris is there, it really stands out as coarse grains of different kinds of minerals, particularly quartz, that normally would not be there in that kind of ocean setting.
You said there was an abrupt shift around 34 million years ago, where you could see Antarctica getting permanent ice. Was the same thing happening in the Arctic? Because you're really talking about global change here, aren't you?
Well, the Arctic has a different history because there's not a continent sitting at the pole. And so the growth of it's really sea ice that grows there instead of a continental ice sheet. A continental ice sheet can build up like in Antarctica today. It's a couple miles thick, right? Which stores a lot of water that's taken out from the ocean and the world's the climate system of the rest of the world. And so when the ice sheet melts in Antarctica, your sea level goes up, right? So the global sea level curve is really nicely shows the sea level drop in the early Oligocene. And of course, in the northern hemisphere, when you do get the buildup of a cold climate and the Arctic sea ice freezes, you also get a continental ice sheet in North America. I should have mentioned that. And of course, the ice sheet advanced and retreated multiple times during the Pleistocene. And, with ice reaching as far as, central Ohio and out to, Massachusetts coastline and so forth. And that also, of course, is going to store a lot of water, which, gets removed from the ocean and causes sea level change as well. And so the shifts in the ice volume can be somewhat in sync between northern and southern hemisphere at various times, depending on how extreme the warming and cooling changes are.
And so you talked about what caused it to get so hot in that Cretaceous interval, and then what caused it to cool down again with carbon getting sort of reintegrated into the seafloor and drawing carbon out of the atmosphere. How did you sort out, say, the puzzle of what happened 34 million years ago?
Well, that's a global story, and it's also a plate tectonic story. And so one of the things I didn't mention is, you've got changes in the position of continents, particularly in the southern hemisphere, that also contributed to the cooling and isolation of Antarctica. One is Australia pulled away from Antarctica initially slowly back in the early Paleogene, latest Cretaceous. It sort of opened up like a scissors from east to west between Antarctica and Australia. And then the Tasman rise opened up, and you got deep circulation between Australia and Antarctica. And about 34 million years ago, you had the southern South America peninsula pulling away from the Antarctica peninsula, and establishment of deep water circulation between those two continents. And so with that, in the fact that Africa already was pulled away from Antarctica, you have what's called the buildup of the circumantarctic current, which is an ocean current surrounding Antarctica and thermally isolating Antarctica. So the circumantarctic current is isolating Antarctica thermally, and that's causing buildup of the ice sheet. And then you have these ice sheets reaching sea level, and ice shelves, as well as sea ice around Antarctica, produce very cold, dense current, which sink into the deep water.
Are you saying then that as the ocean started circulating because of the plate tectonic movements, that drew cold away from Antarctica into other places and contributed to global cooling?
It's one ocean in the world, and so this deep water circulation is called a conveyor belt. So it's really the deep, cold, dense currents produced from ice in the polar latitudes that drives the conveyor belt and mixes the ocean currents. And that mixing happens on the order of, like a molecule of water might take 2,000 years to travel back to where it started. So it's, geologically a rapid process, but for human lifetimes, of course, it seems slow. But it's pretty vigorous. Once you get these ice sheets established, you get very vigorous deep ocean circulation.
Okay, just to clear up the science here, the cooling of Earth that iced up the poles in Antarctica and the Arctic had to do with plate tectonics, movement of the continents, and the patterns of the currents.
And also, from what we heard, with the burial of all the dead plankton, in other words, carbon, that had built up on the ocean floor, which then drew carbon out of the atmosphere, right? Because we know that lower CO2 in the atmosphere makes for a cooler climate. We can see that from what's happening today.
It's a complex system, which explains the difficulty of predicting future climate changes, right?
Well, what's happening now is unprecedented in geologic time in terms of the rate of temperature change and the magnitude. So, we've studied these time intervals of volcanic triggers and ocean temperature change from a number of intervals. And the release of carbon gases, whether it's methane or carbon dioxide, burning of fossil fuels, has happened so fast since the beginning of the industrial age that, we are releasing, in some cases, coal might go back 340, 330 million years ago. Stuff that's been buried in the earth for all these many, many millions of years being released in just a few decades. And that goes into the atmosphere, and it stays there because Earth's organisms aren't able to pull that out of the atmosphere fast enough to sort of keep up. And by deforesting huge chunks of our tropical forests and other parts of the world, we certainly have caused further problems with trying to recapture a lot of this carbon.
So are we kind of going in reverse then from the geologic scale processes you described, which meant that it was really warm and then it cooled down as carbon got incorporated into the seafloor, and now we're kind of exploiting that carbon from the seafloor and pitching it back up into the atmosphere? Are we kind of going backwards?
Yeah, as a colleague of mine wrote in print, we're going back to the Cretaceous. And remember, a lot of this CO2 is coming from coal, and coal has been buried in the earth for hundreds of millions of years. And so we're pumping so much of that CO2 that was buried for these many millions of years and just pumping it into the atmosphere in a few decades. And the data are very clear that we are in a rapid warming, and the rate of CO2 increase is also very rapid and unprecedented.
And what's the Antarctic ice looking like as this sort of reverse is going on?
Well, people have probably noticed in the news, these large ice shelves are breaking up at a faster rate. And so this is because what are called ice streams are moving faster. Antarctic ice tends to be, in the past, tens of thousands of years, sort of frozen to the bedrock. But you get this sort of positive feedback when you get melting, sea level rises, the ice shelves start to float a bit and they melt more, and the bottom of the ice shelves and ice sheets are lubricated, and you get what are called ice streams, and the ice streams start flowing faster. And it's the ice streams that drain the Antarctic ice cap. And those movements are being tracked by satellite. And so there's a clear indication of a couple ice streams that are increasing their rate of movement. And Greenland ice cap is another worry because Greenland is the ice sheets moving faster, the ice streams are moving faster, and Greenland seems to be deglaciating at a pretty fast rate. And so Greenland alone could cause 7 meters sea level rise, which is enough, I think, to cover most of Florida, if not all of Florida. The different climate models have different predictions, but these runaway ice sheet streams can cause very rapid change, and we've seen that in study of the Pliocene and Pleistocene events that have happened in the last million years or so.
So do you think in terms of this scale of foram evolution, if a paleobiologist came along 1,000 years from now and took a look at the forams, would the forams leave a record of this human-caused warming?
Well, they're recording the change in temperature, and if you can measure the changes in decades in sediments that are studied a few centuries from now, yeah, for sure, you'll be able to see this change. I mean, we're looking at how ocean chemistry has changed since just before the industrial age and since that time. And we're also looking at ocean acidification and evidence for that since the industrial age. And, there's areas where it's pretty discernible changes that are occurring. And so within a couple of centuries, judging by the rate at which temperatures are increasing now, this record of warming will certainly be recognizable in the foram record. My hope is, humans put themselves in these corners and fixes and do stupid things, but they also manage to engineer their way out. And my hope is behavior changes, and there's also, some new technologies that allow us to live comfortably but use a lot less energy, a lot less petroleum and coal-based energy anyhow.
So could humans survive on Earth if it was a Cretaceous greenhouse climate? Could they survive in those conditions?
There's plenty of places where the Cretaceous was probably quite comfortable for the dinosaurs and small mammals to live, and I'm sure humans could or would adapt to that. I think more worrisome is what humans do to each other when things get difficult. The fact that people's patience wears thin pretty quickly when they're not getting what they want and what they expect they should have. And so certainly life will go on. Life has gone on through worse cataclysms than the asteroid impact 66 million years ago and other horrible events, at the Permo-Triassic boundary and so forth. So I think life is going to go on, but humans, I'm not so sure. More because we seem to do really stupid things to each other. So it's a question of, how can we pull together as a global community to deal with this? Or if we can't as a global community, at least have enough wise minds to sort of come up with solutions that we haven't come up with yet.
Well, right. And we weren't around for all these other major changes. So the jury's out, really, on our ability to adapt our lifestyles in the face of major global change. Before we close, do you ever get a funny reaction from people that, say, are not familiar with Foraminifera, that are not familiar even with paleobiology? If they ask what you do for a living, do you ever have odd reactions when you try to describe how you're studying these tiny, dead, shelled organisms? to figure out these big problems?
Yeah, there's a lot of surprise that these tiny creatures can tell such big stories. And when I give people tours of my office and show them, what a foram looks like under the microscope, and you see all these different shapes and interesting morphologies, it's a whole different world, looking down the microscope. And when they see I've got this little picking brush and I can take one of those little guys and put it in another container and one by one identify the species, determine the age. It opens eyes to a different world of research that most people have no clue about. And so I've always had this desire to quantify that in a way where we can really give a temperature history and then try to understand, well, why was it so warm? And then when did we switch into the cooling that followed? So this has been a theme throughout my research career, and that is particularly working at southern high latitudes and reconstructing high latitude temperature history.
Have you had dreams about foraminifera? It's okay, you can confess.
When I am pretty immersed in working on a paper, I will dream about, maybe, I don't know about foraminifera, but about the deep past. And so it's puzzle solving, and I call myself a climate detective. And so, I've gone into the deep time at times. So.
Sounds to me like you're a bit of a time traveler. You're a foram time traveler.
That's right.
Great.
All right, Vicki. Well, I gotta ask: if you were a time traveler, what type of time traveler would you be? That's like a she sells seashells on the seashore type. Anyways, what type of time traveler?
So time traveling. So I feel like I would want to go back in time. Would I have to go back and stay there? That's my question.
No.
I could hop around.
Yeah, definitely hop around because like healthcare. So just I don't want to stay anywhere forever.
No. I mean,
appreciate
in the
healthcare.
future doesn't seem great.
Yeah.
In that way. Oh, yeah. Sad trombone.
Oh.
No, I think maybe not too far back. I feel like I would just want to go back and like check out my family when they were younger and see what was going on, because I feel like so much insight that would lend, or even just back short term to see certain situations unfold firsthand.
No, that's a great point. I won't name specific family members. How to do this without doing that? But I dated my high school sweetheart.
High school sweetheart.
I know. Their like her family members knew some of my family members growing up, and would just tell me, if you knew stories about so and so, it would blow your mind. I want to see those stories in real time. That's my answer.
Did they tell you the stories though?
No, they didn't.
That's kind of rude.
Well, see, there's my answer. That's where I'm going.
Okay. What if y'all were at war?
I don't know.
Small town, rural Pennsylvania.
Maybe. All right. Well, we're both going back to spy on our families, essentially. Right. So that's not creepy at all.
No, we're not creeps.
Well, with that, that is all from Third Pod from the Sun.
Thanks so much to Devin for bringing us this story, and to Brian for sharing his work with us.
This episode was produced by Devin with audio engineering from Collin Warren.
We'd love to hear your thoughts on the podcast. Please rate and review us. And you can find new episodes on your favorite podcasting app or at thirdpodfromthesun.com.
Thanks all, and we'll see you next week. Hi, Vicki.
Hey, Shane.
Sorry. No,
I've said hi.
I was like, why is it twice? Why is it hi, Vicki, hi, Shane, hi, Vicki? We're just like going back. Sorry. It's just like I edited this like a half an hour ago. This is the joys of doing this. All right, let's do this again.